Hello everyone, welcome back to your research buddy, and in this video we will talk about most important topics related to semiconductor physics and crystallography. So the first topic that we are going to talk about is direct and indirect band gap. This is the types of band gap, and in our previous video we have talked about the formation of band gap. So band gap is generally the distance between the gap between valence band and conduction band. Okay, so band gap is generally of two types, which is direct band gap and indirect band gap. So let's talk about direct band gap first. So in direct band gap semiconductors, the top of valence band and the bottom of conduction band are occur at the same value of momentum. Okay, it means the top of valence band and the bottom of the conduction band lies in the same value of momentum. It means they are in phase with each other. So we can say that such kind of materials are categorized as direct band gap semiconductors. All right, and in case of indirect band gap semiconductors, so the maximum energy of the valence band occur at the different value of momentum. Okay, so in case of valence band and there is a conduction band, so they are having a different value of momentum at a particular instant of time. All right, so such kind of materials are categorized as indirect band gap semiconductors. So these are the types of band gap, direct and indirect. And next, a small topic we are having is the Fermi Dirac distribution. So as we know that we have valence band and conduction band, and we are generally say that number of electrons are or number of holes are present in valence band, and at the normal temperature, at the equilibrium temperature. Okay, so how we can probabilize how much amount of particles or charged particles are present in any state, either in valence band or conduction band? We need to use a Fermi Dirac distribution. Generally there are two types of distributions. One is the Bose-Einstein distribution, which is used for the bosonic particle which are having integral spin. But in case of electrons and related to particles having property like electrons, they are having half integral spin. So in that case we need to use Fermi Dirac distribution. Okay, so Fermi Dirac distribution applies to the fermions. Fermions are having half integral spin, and the example is electron. Okay, so Fermi Dirac distribution applies to the fermions uh, with half integral spin, which must obey Pauli exclusion principle. Okay, so this Fermi Dirac distribution, this distribution must obey Pauli exclusion principle, and according to this principle, no two electron can exist in a same quantum state. All right, so each type of distribution function, whether it is Fermi Dirac or Bose-Einstein, has a normalization term multiplied the exponential in the denominator, which may be temperature dependent. Okay, so any type of distribution having this scenario, that each type of distribution function has a normalization term which is multiplied to the exponential in the denominator, which may be temperature dependent. And in case of Fermi Dirac, the term is written as exponential EF over KT, and here we are having minus. All right, this is for Fermi Dirac, where EF is equals to Fermi energy. Okay, EF is Fermi energy, K is Boltzmann constant, and T is the temperature. Okay, in Kelvin we are taking. All right, now we have a concept of Fermi energy. Here we have talked about Fermi energy, so let's have an idea about what is Fermi energy. Fermi energy. So Fermi energy, before starting with Fermi energy, let's talk about Fermi level. Fermi level. Fermi level. So Fermi level is the highest kinetic energy that can be achieved by an electron at an absolute zero temperature. Okay, absolute zero temperature पे the maximum amount of energy that can be achieved is called Fermi energy. Okay, and that is called Fermi level. And in case of Fermi energy, at an absolute zero temperature, the highest kinetic energy that can be achieved by an electron is called Fermi energy. Alright, okay, so in case of Fermi-Dirac distribution for fermions, so we can write Fermi-Dirac distribution for this fermions represented by FFT, or also function of this Fermi energy is equals to 1 upon exponential E minus EF divided by KT plus 1, right? So here we have a complete Fermi-Dirac distribution derivation. Okay, by using this equation we can find out, or we can probabilize the amount of either electrons or holes in any state, either in valence band or conduction band, or also in Fermi energy or Fermi level. How much electrons are present there, we can probabilize by using this equation. Okay, so this is about Fermi-Dirac distribution, and let's define the components here. So here EF is equals to Fermi energy. Here EF is equals to Fermi energy, K Boltzmann constant having value 1.38 into 10 raised to power minus 23 joule per Kelvin, or also 8.6 into 10 raised to power minus 5 electron volt per Kelvin, right? And here T is absolute zero temperature, or absolute temperature, not zero, as absolute temperature in Kelvin again. All right, and this equation can also be written as, so we can write this equation by putting 1 by KT as beta. So let's say this is my equation number 1. So equation 1 can be written as by taking Fermi-Dirac function is equals to function of energy is equals to 1 over E exponential E minus Fermi energy multiplied by beta, where beta is equals to 1 over KT. Alright, now we have some cases in case of Fermi energy. So we have cases. First one, when E is equals to EF, this energy, the total energy of the system is equals to energy, Fermi energy, then exponential term, that is exponential E minus EF multiplied by beta is equals to 1, right? In that case, the modification we can do in this equation number 2 will be, so the equation number 2 will become Fermi-Dirac is equals to function of energy is equals to 1 by 2. All right, and second case, when in the limit Okay, so we are having a limit, that is temperature T is equals to 0. So in that case, equation number 2 can be written as, by using this T is equals to 0, this Fermi energy, function of total energy, either 1 or 0 for, if E is less than EF, we will get this 1, and 0 for is greater than EF. Third case we are having is at T is equals to 0, fermions occupy the lowest energy state. Okay, so these are the important points related to Fermi Dirac distribution and Fermi level. So fermions occupy the lowest energy state. All right, and fourth point is the temperature higher than this absolute zero temperature, there is little chance that thermal energy will kick the fermions to an energy greater than EF. Okay, so in that case electrons will move to the conduction band, because we have a valence band, and then we have the position of Fermi level, and then there is a conduction band. So we have, in generally we can denote this as, we have valence band and there is conduction band CB, and in somewhere in between valence band and conduction band there is EF, Fermi energy. Okay, so if the temperature greater than absolute zero temperature, there is a chance that thermal energy will kick the fermions from this valence band and to the energy greater than EF. So it means greater than EF, they will move to conduction band. So this is about Fermi energy and Fermi level. All right, so in next video we will talk about the position of Fermi level in pure semiconductor or intrinsic semiconductors. Okay, so that's all for this particular video. If you have any question, you can comment below. Thanks for watching this video. I'll see you in the next one. Thank you.